So for these first couple pages of physiology, I had already done highlighting before I realized that it would be nice to have the videos for a second review before making flashcards, just to listen to while crocheting or cleaning or something, knitting, whatever. So I'm going to pretend to underline so that I get the kinetic experience in my body, and then it's just a couple pages, so we'll be back to normal soon. Alright, cardiovascular physiology. Functions. It's a muscular pump for blood circulation, 5 to 6 liters per minute in a 70 kilogram man. Endocrine. ANP, atrial natriuretic peptide, in response to increased atrial pressure. BNP, B-type natriuretic peptide, in response to overstretched ventricles. Cardiac muscle. Involuntary muscle with cross striations. Individual cells are connected by intercalated discs, which allow for cell adhesion. Intercalated discs allow the heart to contract in synchrony as one unit, syncytium. There are gap junctions in the discs, which allow for passage of ions between the myocytes. These gaps allow action potentials to spread easily between the cardiac myocytes. Cardiac muscle contraction. In the resting state, there is more sodium and calcium outside, and more potassium inside the cell. Phase 0. Sodium influxes into the cardiac myocytes, causing rapid depolarization, the upstroke. Phase 1. Closure of the sodium gates. Potassium gates open, with potassium efflux, initial repolarization. Phase 2. Calcium influx through L-type calcium channels, the plateau phase, phase 2. Potassium efflux is stopped in the plateau phase. Phase 3, inactivation of calcium influx with the continuation of potassium efflux, rest of polarization. So phase 3 is like the second half of repolarization. Phase 4, removal of excess sodium and calcium with restoration of the membrane potential. The sodium-potassium ATPase pump pushes sodium out and brings potassium back into the cell. 3 sodium for every 2 potassium. The amount of intracellular calcium determines the force of contraction of the cardial cell. Here's a chart of the phases, electrical changes in ventricular fibers. Phase 0, phase 1, phase 2, phase 3, phase 4. Alright, next section. Refractory periods. Absolute ARP. No action potential can be initiated regardless of the stimulus strength because the sodium channels are closed in phase 1 through to mid-phase 3. Relative RRP. An action potential can be elicited, however, a greater stimulus is needed. It extends between the middle of phase 3 to the start of phase 4. Cardiac muscle is incapable of sustained contraction, tetany, unlike skeletal muscle, because of the longer absolute refractory period. So the longer absolute refractory period prevents tetany in the heart muscle. Starling Law, cardiac output is directly proportional to venous return. Force of contraction of a myocardial fiber, stroke volume, is proportional to the length of the myocardial fiber, equivalent to the end diastolic volume. The greater amount of blood returning to the heart during diastole, venous return, the greater the stretching of the cardiac myocytes. Venous return is the most important determinant in this law. Greater stretch results in a greater force of contraction, causing an increase in the cardiac output, volume of ejected blood from the heart per minute. Cardiac cycle. First heart sound is due to the closure of tricuspid and mitral valves. Lub is closure of tricuspid and mitral. Second heart sound is due to the closure of the pulmonary and aortic valves. Dub. Excuse me. Third heart sound, just after the second heart sound, is seen in congestive heart failure. Dub up. Fourth heart sound is heard before the first heart sound. It's caused by a powerful atrial contraction and may be seen in hypertrophic cardiomyopathy. Below. Systole is a contraction. Occurs between heart sounds 1 and 2, approximately a third of the cardiac cycle. Diastole, relaxation, occurs between heart sounds 2 and 1, approximately 2/3 of the cardiac cycle. Alright, next page. The following pressure changes occur in various chambers and great vessels. Right atrium, 0 to 5 millimeters per mercury. Right ventricle, 5 to 25. Pulmonary trunk, 10 to 25. Left atrium, 5 to 10. Left ventricle, 10 to 120. Aorta, 80 to 120. 80% of blood flows into the ventricles passively. The remaining 20% is due to contraction of the atria. During the cardiac cycle, there are 3 waves in the pressure in the right atrium. The A wave coincides with atrial contraction. The C wave coincides with the right ventricular contraction, with the bulging of the tricuspid valve into the right atrium. The V wave coincides with atrial filling against a closed tricuspid valve. During ventricular contraction, the pressure builds up with the closure of the AV valves and when the aortic and pulmonary valves are open. The blood is ejected into the circulation. This occurs in 4 phases. Oops, fix the camera. Isovolumic contraction, increase in pressure without change in volume, which occurs between the closure of the mitral valves and the opening of the aortic. First mitral, then aortic. Ejection, only 70 mL of the 120 in the ventricle is expelled. Ejection fraction. Isovolumic relaxation, decrease in the ventricular pressure without a change in the volume. This occurs between the closing of the aortic valve and the opening of the mitral valve. The filling phase, during which blood enters through the opened AV valves. Okay. Electrocardiogram, also known as EKG, because German as a language. This reflects the electroactivity in the heart as the impulse is generated in the SA node. The initial impulse is generated by the SA node, which has its own intrinsic rhythmicity of around 80 to 100 times per minute, which is the rate of depolarization. The impulse spreads through the intraatrial bundles, causing both atria to contract simultaneously. The impulse is spread to the ventricles from the SA node to the AV node, which also has its own intrinsic rhythmicity of around 40 to 60 times per minute, rate of depolarization. When the SA nodal rhythm is superimposed upon the AV nodal rhythm, the heart rate is 70 beats per minute. The impulse from the AV node is passed down through the bundle of His into the right and left bundle branches, which are located in the muscular part of the interventricular septum. The rate of depolarization, beats per minute, is fastest in the SA node and slowest in the Purkinje fibers. Conduction velocity, speed measured in meters per second, at which action potential is transmitted, is slowest in the AV node and fastest in the Purkinje fibers. P wave represents atrial depolarization and precedes atrial contraction. PR interval extends from the P wave to the start of the Q wave. Conduction is delayed through the AV node, and this allows for the ventricles to completely fill. QRS complex represents ventricular depolarization, less than 120 milliseconds. QT interval is the time required for ventricular depolarization and repolarization, represents systole. ST segment extends from the end of the S wave to the start of the T wave. T wave represents ventricular repolarization. Occasionally, a U wave may be present due to the papillary muscle repolarization or hypokalemia. Atrial repolarization is not seen on the ECG because it is buried by the QRS complex. First-degree AV block causes a prolonged PR interval. Second-degree AV block, Mobitz type 1 or Wenckebach phenomenon, causes progressive prolongation of the PR interval with drop beats. Third-degree AV block, P waves are not followed by QRS complexes. And here we have this little chart. Blood volume distribution. Veins are 60%. They are the capacitance vessels. Arteries and arterioles are 20%. Lungs 10, heart 5, capillaries 5. Alright, that's it for this video. Take a look at the whole page here.